Okay, so right, as we just said, I want to come up with another model that can figure out the where the electrons are in the atom, but not use the orbital energy diagram because, like I said, it gets a little crazy once you get in energy level 4. Okay, so let's talk about orbital energy diagrams just for a second. Orbital energy diagrams tell us the most information of any model. It gives the energy levels, the subshells, the orbitals, electrons, and the spins. Okay, but do we need all this information to figure out where the electrons are? No, we don't. We have other ways of doing that. And what we're going to do is we're going to develop a model that can do that. All right, and the way I'm going to develop this is by, first of all, looking at the periodic table. So this periodic table has 118 elements. And what we're going to do is just kind of focus actually on the first 3 rows. So we're going to chop off anything below energy level 3, so all of this. And then what we're going to do is we're going to squish row 2 up with row 13, because that way number will go 3, 4, 5, 6, 7, 8, and so forth. And so when you do that, you end up getting this arrangement. Okay, so we got a tiny little periodic table that only looks at the first 18 elements. Okay. Right. Now what we're going to do is kind of similar thing with the orbital energy diagram. So we're going to take the first 3 energy levels, and then we're going to chop off the D's, okay, for now, and then just look at this section here, the S's and the P's, energy level 1, 2, and 3, and the S's and the P's. And then what we're going to do is actually split up each orbital into sides where one side you can put up and you can put it down. So you can put it up here and down here, up, down, up, down, up, 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 and so forth. Okay. So energy level 1, 2, and 3, S subshell, P subshell, and there's 3 orbitals. Each one can put 2 electrons. All right. Okay. So what we have is this. Okay, what we're going to do is take boron. And so boron's orbital energy diagram is the following. You put, so it has 5 electrons, up, down, and then up. Okay, now if we go over here to the periodic table, and we could, if we represent the arrows, so you put arrow here, arrow here, arrow here, arrow here, you can see that these arrows, putting the arrows in order in the periodic table, puts them in the same spot it does as the orbital energy diagram. So what we do is we just flip this guy upside down, and we get this right here. You can see it's exactly the same as this up here. Well, this should be up here, but basically, so it has 2 here, 2 here, 2 here, and 1 here, 2 here, 2 here, and 1 here. So does the periodic table, is it the orbital energy diagram? Okay. So we'll take a look at carbon in a minute. But can I go up, down, and then up, up? Okay. Is the periodic table just another, is it nature's orbital energy diagram? Okay. Right, so what we got actually is, what we can do is we can overlap these two because they're the same so far, it looks like. Okay, so it looks like so these are energy levels which correspond to the rows, and these represent the S. So this is like a S orbital, S orbital, S orbital, and then you have your P's. Okay, and there's 3 sets, kind of looks like. All right. All right, so let's see if it works with another atom. So let's try carbon. So carbon has 6 electrons, So it goes up, down, and then up. All right, excuse me, things keep on happening. Okay, power just died. Okay, all right, so back to what I have here for carbon. So this, the upside down OED using the periodic table. So it goes up, down. So these are S, up, down. And then when we did carbon, it went, so this is the orbital, this is the orbital, and this is the orbital. Go up, up. And notice it doesn't fall where it's supposed to, okay? It falls on nitrogen. Okay. Does that mean we can abandon? All right. So using the periodic table does work to find the orbital energy diagram. It worked for up to boron. It'll work for hydrogen, helium, lithium, beryllium, and boron. But after that, it won't work. But it does give, for carbon, it did give the right energy level, and it did put it in a p subshell. So it did say that the last electron of carbon went into energy level 2 and a p subshell. It didn't give the right orbital or the right spin, but it gave the right energy and the right subshell. So maybe what we're going to do is use a periodic table and just kind of forget about the orbital and spin, and that's what we're going to do. So what we're going to do is develop a model. It's called the electronic configuration model, EC. That's going to focus on just the energy level and the subshells and how many electrons are in the subshells. And from that, it will give us the valence shell and the valence electrons, exactly what I want. Okay, and we'll see how the periodic, we already saw that the periodic table and the orbital energy diagram are connected, but we'll see it again in a minute. Again, for orbital energy diagram, I just want you to be able to do the first 18 elements. But for this model, you're going to have to be able to do more, up to 56 elements. Okay. And so let's get into doing this model. Right. First of all, we're going to use the orbital energy diagram to come up with the electronic configuration. And then from there, we will transfer to figure out the electronic configuration from the periodic table. Okay, so this is calcium. All right. We developed this at some point in the past. Okay, I can't remember where I did this. Okay, but so this is calcium, and calcium has so this is the orbital energy diagram, and so once you get the orbital energy diagram, what you do is just circle the subshells, not the squares. Okay, it turns out the S subshell, when you circle the square, you're circling the subshell as well, because the subshell is the orbital. Okay, then I circled the P subshell, and then S. So energy level 1 has the S subshell, so I circled that. Energy level 2 has a S subshell, I circled that. It also has a P subshell, so I circled that. And it has a 3. And then what you do is you write down the energy level, the subshell, and then how many electrons are in the subshell. So write down 1, S, and 2 arrows. So 1S, 2. It's not squared, okay? It's superscript. And then it has 2, S, 2. And then it has 2, P, and there's 6. And then finally 3, S2. So this is the electronic configuration of calcium. Okay, from this you can see its valence shell is 3, and it has 2 electrons in the valence shell, so 2 valence electrons. So the highest number is the valence shell, and how many electrons are in the valence shell is how many valence electrons it has. All right, now let's do oxygen. So oxygen has, so we did the oxygen already, go back and look. So it has 8 electrons, up, down, up, down, up, 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 down, okay? All right, so what you do is you circle the subshells, so S, S, and the P, and then you write down, so you write down 1 S, and there's 2 arrows. Okay, then you write down 2 S and 2 arrows, and then 2P 6. Because there's, I mean not 6, 4 arrows. Okay, so the valence shell is 2, and it's actually in 2 spots. Because there's a 2S and a 2P, and there's a total of 6 valence electrons. There's 2 here, 1, 2, 3, 4, 5, 6. 2 plus 4 is 6. So don't forget about the S, 2S. Sometimes students just write down the 4 because it's the last one. You have to include any one that has a 2 here. It works. Okay. All right. So what we're going to do is now we're going to relate the electronic configuration to the periodic table. And this is going to take some practice, and hopefully the diagrams I have and the way I'm going to explain will help. All right. Okay, first of all, what we saw from at the beginning of this is that the periodic table kind of can relate to the orbital energy diagram. The first 2 columns are like the S subshells. And then we showed is that these guys out here were like the P subshells, okay? And so what we're going to do is expand on that. Okay, so the first 2 columns represent the S subshell. The last 6 columns represent the P subshell. Okay, a P subshell has 3 orbitals, and each orbital can have 2. So 3 times 2 is 6. So that's why there's 6 here. Okay, this middle section represents the D subshells. Remember, the D's have 5 orbitals, and you can put 2 in each one, so there must be 10. So if you count across, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, just a little thing here. Notice this it goes from 57 to 72. That's because there's some elements down at the bottom that I left off, and we're not going to deal with those. All right, so there are basically 2 components at the periodic table. The periodic table can tell us the energy levels and the subshells, just like we talked about, and it also could tell us how many electrons. And that's exactly what we need to know for electronic configuration. Electronic configuration tells us the energy level, the subshells, and how many electrons can go in the each subcell. Go back and just look at oxygen. When we figured out each one of the subshells, the energy levels, and then how many arrows were in each subshell. And that's what we kind of do here, but not use the orbital energy diagram, but the periodic table. So let's start out with oxygen, okay? And we expect to get 1s2, 2s2, 2p4. So first thing you do is you find oxygen on a periodic table. And it's right here, I put a star around it. Okay, and what I'm going to do is you got to this is basically where we're going to say the oxygen lives. It has an address. Okay, and its address is row 2. So you write down 2. You write down which sections it's in. It's in 2p, and it's 1, 2, 3, 4. So its address is 2p4. So you write that down. And notice it's exactly as the last number here. Okay, what we're going to do next is figure these two out. Okay, so what you've done is you've figured out where this guy lives. It lives in the 2p's and it's 4 over. What we have to do now is figure out the other two components of this. Okay, so next thing we do is going to work backwards. So what you do is you go over to the next, move over to the next subshells, S's, and that's what this green arrow is, and you go through it. So this is the 2s, so it's row 2s, and you go through 2 squares, so you write down 2s and you go through 2 squares, 1 2, and then what you do is you go up. So the idea is you go up and across, okay, and finally get up at the top. And so you end up getting here, go through these two, through the 1s, and you go through 2, 1s2. So you have 2p4, 2s2, 1s2. Okay, and you can write it down, 2p4, 2s2, 1s2, which is the reverse of what we had. Okay, and you could flip it if you want to 1s2, 2s2, 2p4. Either one is fine. The key thing is it gives you the orbital energy diagram, and it tells you how many valence electrons in the valence shell. Okay, so we're going to expand on this and do some more, and you probably want to listen through this more than once. Okay, now what we're going to do is do calcium, and we've already know calcium is 1s2, 2s2, 2p6, 3s2. Sorry, it should be 1s2, 2ps2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay. All right. So what you do is you find out where the calcium is, and you write down where its address is. It's in row 4 in the S's, and it's 2 over, so it's 4s2. All right, so that's the first thing you do. You write down 4s2. Okay, now what we want to do is we want to get up. Sorry, pen isn't working. So what you want to do is you want to get up to here. Okay, the hydrogen area. Okay, so you just can't jump up. You have to go from 20, 19, 18 all the way across. So what you do is you have to go through this section next. So from section 3, from this section right here, 4s, to the previous section up to here, and then you go, so you're in 3p, and you go over 6, so you write down 3p6. Okay, so you have 4s2, 3p6. Okay, now you go across, and now you're in the s's, and this is going to be 3s2, and there's 2 squares, so write down 3s2. And you come up over here and go through the 2p's, and there's 6, 2p6, 2s2, and then finally 1s2. Okay, so from the 4s, you'll go up to the 2p, through all 6 of them for 2p6, then go across to the 3s2, and then up across to the 2p6, and across 2s2, and up to 1s2. And so you get 4s2, 3p6, 3s2, 2p6, 2s2, 1s2, just like you expect. Valence shell is 4, 2 electrons in the valence shell. Okay, sulfur. So sulfur is element number 16. Okay, and it's found in row 3 in the p's and 4 over. So you write down 3p4. Okay, then you go over to the next subshell, go to the previous section, 3s, so move across over here and write down 3s2. Then go up, go to the next previous section, the 2p's, and go across, 2p6, go across, 2s2, up, across, 1s2, and there you go. So the valence shell, sulfur is 3, 3 and 3, and remember it has 6 valence electrons because there's 4 in a p and 4 in a 2, add them together is 6. So there's 6 valence electrons here. Alright, next thing we're going to do is expand our model to d electrons. I told you that using the orbital energy diagram for potassium, calcium, that just got too complicated, and that's why we're using this one. And we haven't done anything with the elements in row 3 through 12. So let's get, and the reason why we haven't done that is because the orbital energy diagram is just too complicated. And we'll see that the electronic configuration will give us the right answer, but there's going to be some twists that we have to be careful about it. And what we're going to do is start out with iron. So iron has 26 electrons. So you find our bond at periodic table. Okay, and it's found in row 4. It's in the D's now, and it's 6 over in the D's. 1, 2, 3, 4, 5, 6. Don't count all the way across. It's from the D's. So 1, 2, 3, 4, 5, 6. Okay, now you expect from what we've done is you should write down 4d6. Well, that's not right, because if you go back to the orbital energy diagram, the first place that we encounter d subshells is energy level 3. Energy level 1 had an S, energy level 2 had an S and P, energy level 3 had an S and P and a D. So in this case, where the D's are not really their energy level. And so what they are, any of the elements in the D section are actually one less, their energy level is one less than the row they're in. So iron is really in the 3d6. So the D's are one less than the row they're in. So 3, so because it's in the D's, it's one less than 4, 3. It's in the D's, and it's 6 over. So it's 3d6. So let's continue with iron. So after that, it basically follows the same pattern. So you write down 3d6. Okay, but now we're into 4s's, and you go 2 over, so it's 4s2. Okay, then you come up to the 3p6's, go across 3p6, and go across 3s2, up 2p6, 2s2, 1s2. And so I wrote it down the way I just figured it out. 3d6 first, 4s2 second, 3p6 third, and so forth. If you want, what you could do is you could rearrange this so that's 1s, 2s, 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2, or you could just leave it the way it is. Just want to make sure that everybody is there. What's a valence shell? 4. Okay, it's not 3. Okay, because this big number, 4 is the biggest number you see here. So the energy level, highest energy level is 4, which is the valence shell. And it has 2 electrons in it. Okay, so this is the way you could draw it, write it out. You could write it out just the way I showed you. Or if you want, you could rewrite it so the 4 is in front of the 3. Or you could flip it like this. Any one of them. So this is the way that I figured it out, but I rearranged it so it's in order of the energy numbers and doesn't matter. You could have it this way, or this way. This last one, it shows you it's kind of the best way because you can see, makes kind of more sense. And it also shows you that 4 is the highest here, and it has 2 valence electrons. Now another thing about this is if you want to check to see if your answer might be right, what you do is you add up all the superscripts. And if the sum of all the superscripts equals to the number of electrons, you probably got the right answer. So if you get 2 plus, so you go 2 plus 2 plus 6 plus 2 plus 6 plus 6 plus 2, okay, that equals 26. And iron has 26, so that's a good check. All right, so we're going to do 3 more of these. And so we're going to start with bromine. And so bromine is number 35. It's in row 4. It's in the P's. So, okay, so so you don't have to worry about subtracting 1. So, and it's 1, 2, 3, 4, 5 over. So it's 4p 5 over, so write down 4p 5. So I'll wrote that down first, 4p 5. All right, so yeah, next you're going to go through the 3 D's, and you write down all squares you go through, so you write down 3d10. Then you go through the 4s2. So you're done with all row 4. Then you go up to row 3, go through the 3p6 and the 3s2. Then you go up to 2p6 and 2s2, row 2. And then row 1, 1s2. So the key thing is go through each row. Once you get through this row, you jump up to the next row, jump up to the next row, and then finally this row. And you're always starting from the right hand side. So you're going to go finish with go from right to left, come back, right to left, come back, right to left. And you're going to go through each section. So what you have here is 4p5, then go through this section 3d10, go through this section 4s2. Then go through 3p6, 3s2, 2p6, 2s2, 1s2. And here's how you can write it down. Just like the way I developed it, 4p5, 3d10, so forth. The highest energy level is 4, here and here. And there's a total of 7 valence electrons, 5 from the P and 2 from the S. So the valence shell is 4, and there are 7 valence electrons. Okay, now strontium. So strontium is number 38, and it's row 5, it's in the S's, and it's 2 over, 5s2. Right, so we're done with row 5. So you go across, that's the 5s2. Now you come up to row 4 and you do all row 4. 4p6, 3d10, 4s2. Go up to row 3, 3p6, 3s2. Row 2, 2p6, 2s2, 1s2. Write that all out, and that's what you get. Okay. It has 2 valence electrons in the 5th level, so the energy level 5 is the valence shell, and has 2 valence electrons. Okay, then ruthenium has 44 electrons right here. It's in the D's, so be careful here. So it's in row 5, but it's in the D's, so that really means it's 4. 4D, and it's 1, 2, 3, 4, 5, 6 over, so it's 4D6. So that's the first one. Okay, then you go, keep in the same row, then you go through the 5S's, 5S2, up to the 4s, 4P6, 3S2, 4S2, 3P6, 3S2, 2P6, 2S2, 1s2. So like I said, you finish, go from right to left, finish up the row. Make sure you get the subshells right. The D's are one less than the row you're in. So this is actually, even though it's row 5, it's 4 D's. And 6 over 4D6, 5s2, and so forth. You can write it out like this. Valence electrons are 2. And highest energy level is 5. Even though we started out with the D's, okay, it's not the highest energy level. The highest energy level is the 5s, okay? So even though we wrote down 4d6 maybe first, it's not the highest energy level. So you look at the number in front. The highest number is the energy level, valence shell, and then it has 2 valence electrons. Okay, the elements that are in the D section are called transition elements. And it turns out that by using this method, no matter which element you choose in the transition elements, all the D atoms will have 2 valence electrons using this model. Okay, you go through them all, but they all have 2 valence electrons. Now, in reality, that's not always the case. For instance, copper and silver, they don't really have 2 valence electrons. They only have 1. But we're not going to worry about the exceptions. So anytime, all transition elements will have 2 valence electrons. And if you look, you could maybe figure out why that is. Okay, so let's see what the main features of these two models are. What are the key things we distill from these models? Okay, first of all, if you go back and look carefully, and if you don't want to look carefully, I'm going to tell you, okay, is all the valence electrons will always be in the S and P subshells, never in the D. Okay, because an S subshell has 2 spots and a P has 6, the maximum number of valence electrons is 8. So the highest number of electrons that can be on the outer shell of an electron are 8. Okay, and that's just because the model makes it that way. The model forces it to be always being 8, the highest number being 8. And there's no other reason. You might learn that if you ever had chemistry before, it says there has to be 8 electrons in the outer shell because of stable stability, whatever. It's because the model tells us this. The model gives us that the maximum number of electrons you can have in the outer shell is 8. And so if we look at the periodic table, column 1 has 1 valence electron. You go back and look, lithium, sodium, so forth, they all have 1 valence electron. And so if you go through them, column 2 has 2. All the transition elements, column 3 through 12, have 2 valence electrons. We just said that. Column 13 has 3, 14 has 4, and so forth. Okay. Right. Also, the valence shell of an element is always going to be the row that it's in, even if it's a transition element. Okay, so whatever row an element's in, you know automatically what its valence shell is, and also you can figure out the number of valence electrons by this pattern here. Column 1, 1, column 2, 2, 13, 3, 14, 4, and so forth. Guess what? That's all that's really important for us to know about an atom structure is what its valence electrons are and what its valence shell is. Okay, So that's exactly what we want to do.